When you dissolve one material in another, then you actually change the property of the mixture from what it was before. So an important place that this comes up in cooking, and in fact in the lab that you will do this week, is when you make ice cream. So making ice cream involves dissolving both sugar in water, or actually dissolving sugar in milk, and dissolving salt in water, which is how you make the ice to cool the milk to make it into ice cream. We just talked about the dissolution of sugar and salt in milk, and you'll recall that there were several striking properties. First of all, you could dissolve much more sugar in water than you could salt when you measure it by weight. So there's about a 6-fold difference of the mass of sugar that can be dissolved in a pound of water than the mass of salt. But we also said that this difference was explained by the different molecular weights of sugar and salt, and actually the number of molecules that you were dissolving in the same volume of water was about the same. So imagine now that you took either a pound of salt water or a pound of sugar water, and suppose that they were both saturated with the solute, so you couldn't put any more in. And imagine that we now try to have this water have a phase transition of some type. So we could either try to freeze it, or we could try to boil it. So since we're thinking about ice cream at the moment, let's imagine freezing it. If we cool it, then we know that without the sugar or salt, the temperature at which the water becomes a solid is 0 degrees Celsius. And that's because that's the temperature when the entropy of the water molecules moving around becomes balanced by the sticking energy of the water molecules to each other to make the crystal. If there's salt or sugar in the water, that salt and sugar has an additional entropy. That is, besides the entropy of the water molecules, there's also an entropy of the salt molecules. So you can imagine these little molecules jiggling around. And when you freeze the mixture, you have to also stop the motion of the solute molecules, of the sugar or salt. And that requires a little extra energy than you would have had to give it otherwise. So this extra energy leads to the phenomenon that people call freezing point depression. This is the notion that if you actually try to freeze a mixture of salt water or sugar water, you have to actually go to a lower temperature to freeze it than you would if there were no salt and sugar. That lower temperature is to actually put in to get rid of the extra energy that's needed to actually stop the solute from moving. Freezing point depression essentially depends on the entropy of the solute, and as such, the amount that you have to actually depress the freezing point really depends on the number of solute molecules per unit volume that you've managed to put in. The more you put in, the more the freezing point is depressed. Now, freezing point depression is an important phenomenon here in Boston during the winter because we tend to pour, for better or worse, salt on the roads, which of course stops the water that is falling from precipitation from freezing and makes the sidewalks and the roads less slippery. If we think about this when making ice cream, it raises a bit of a conundrum. So if you make ice cream, you'll all recall, or you will know soon enough when you do the lab, that the recipe for ice cream essentially involves taking milk, which of course has little fat globules and other things in it. It's basically water with fat globules and other molecules. And you then pour sugar in the milk because you would like it to be sweet. And then you need to freeze the sweet milk. Now, if you freeze the sweet milk by surrounding it by just normal ice, just normal frozen water, it won't freeze. And the reason is because of freezing point depression. The mixture has a lower freezing point than the water. So somehow you have to get the material that's around the milk with the sugar in it to have a lower freezing point than that of the milk. And a way to do that is to add salt. So if you add salt, you will, of course, depress the freezing point of the salt water. If you then freeze that, it will have a lower temperature than the freezing point of the milk sugar mixture, and that will allow you to freeze it and make ice cream. Now, if you think through it, there's only one potential flaw in my argument, which is that you need to make sure that the freezing point of the sugar-milk mixture is in fact higher than that of the salt water. So typically ice cream recipes, and certainly the one that we've told you to do, what you do is you try to saturate the water with salt. So you put in 1/3 of a gram per gram, or as close to the maximum that you can, because that will give you the maximum amount of freezing point depression and will make the salt water as the ice when salt water freezes as cold as it can. Now, you'll recall that when you pour sugar in water, the amount of sugar that actually your taste buds taste as being sweet is actually far below the solubility limit. So I didn't tell you this, but you can all now go and look at your can of Coca-Cola that you're drinking and see how much sugar is in it. And although there's an appalling amount of sugar in the Coca-Cola that you drink, it's actually much, much less than the solubility limit. And what that means is that the amount of freezing point depression that there will be in the milk with sugar in it is actually not nearly as much as in the salt water, and that's why the ice cream recipes tend to work. Solutes not only lower the freezing point of mixtures, they also raise the boiling point. The physics of this is really very similar, and this is equally important for cooking, although, as I will tell you, a different type of cooking. So let's imagine that we have sugar water again. Let's just go back to our candidate example where we've poured 2 pounds of sugar in 1 pound of water, and the sugar molecules are whizzing around. And now imagine we try to boil the mixture. So when we boil the mixture, actually, what's going to boil off is the water molecules, not the sugar molecules. And thus, you're going to decrease the number of water molecules that are around for the sugar to hang out in. That's going to decrease the entropy of the sugar, because the sugar is going to have less places it can be. I mean, if there's a lot of water for the sugar to be in, then it's got every sugar molecule has lots of room to roam. Whereas when you get rid of some of the water, there's less room to roam. So the entropy is going to decrease. The consequence of that is that if you want to boil the mixture of sugar and water, you have to actually heat it up to a hotter temperature than you would if there were no sugar in the water. And this phenomenon is called boiling point elevation. It's quite analogous to freezing point depression, and it's basically true with all solutes that are dissolved in a solvent. When you ever put stuff in, you always have to, the boiling point will always go up above what it was without the solute, and the freezing point will always go down. How is boiling point elevation important for cooking? So to explain this to you, or to explain at least one instance of this, what I want to show you is a plot of the boiling point of a sugar-water mixture as a function of the concentration of sugar that's dissolved in it. When there's no sugar, of course, the boiling point is 100 degrees Celsius. But as you increase the percentage of sugar by weight that's in the mixture, the boiling point goes up dramatically. By the time that you're at around 80% of the weight is sugar, the boiling point has gone up to 110 degrees. And as you continue to increase the weight percent of sugar, the boiling point goes up more and more until at about 100% sugar, that is when there's almost all sugar, the boiling point is 150 degrees. So the boiling point is actually elevated by about 50 degrees Celsius between no sugar and essentially all sugar. So this plot actually contains within it the secrets of candy making. Why? So imagine that you wanted to make candy. So typical candy recipes involve dumping as much sugar as you can into water and then starting out by boiling the mixture. When you boil the mixture, then of course what you're doing is that you're evaporating off some of the water, which basically means that you're increasing the percentage of the sugar that is in the mixture more, which means that you've, according to this plot, raised the boiling point even more, which means that you're going to boil off even more of the water, which will then raise the boiling point more. And if you continue to add heat to it, that will cause more of the water to boil off, raising the boiling point even more. And you see that as time goes off, you're going to boil off more and more water. The mixture will get hotter and hotter, and you will tune the percentage of sugar that's in the water. And indeed, when you cook candy, and when we describe how to cook candy in this class, you will see that you have to use a candy thermometer to very, very accurately measure the temperature of the mixture as the initial step towards making the candy. And what this plot shows you is that what you're actually controlling with the temperature of the candy thermometer is the weight percent of sugar that is in the mixture. And the weight percent of sugar controls the texture of the sugar, it controls what can be made out of the sugar, and is really at the core of candy making.